Looky what we have here. This is the Philips DSS930. And it shows my age and shows their age. Plastic ring is just falling off. Brilliant. These things are well over 30 years old. And what's so special about them is that these are not normal loudspeakers, they're active. And they're not just active, they're digital. So what they do is they take a signal in over SPDIF, or in this case really PDIF, because Philips sort of hacked the signal. The signal goes from a player to one loudspeaker and then from one to the other, and you set them on the speaker to decode the left or the right channel, which is nothing special today. I've built systems like that, they're in production, but this was 30 years ago. So this high-end Philips stuff from the 1990s, I think, was them at their best. It was only 10 years after the introduction of the CD and digital sound, which was perfect audio forever, as we all perfectly know. But this came very shortly after the introduction of the bitstream components. Sigma delta modulation, or noise shaping, or bitstream, was invented in the late 70s because the best DA converter that Philips could build for digital audio had a resolution of 14 bits, and that was a direct scaling of current sources in a 2 to the power of n fashion. And they couldn't do better than 14 bits, so in order to get to the full 16-bit, which was what Philips insisted on for the CD standard, they had to invent 2 more bits of resolution. And because they couldn't get them physically, they decided to go with an oversampling technique. 4 times oversampling plus a digital filtering and some noise shaping gave them 2 extra bits, so that the effective number of bits was 16 and the dynamic range was 96 decibel. The TDA 1540 was a 14-bit DAC, and the noise shaping and the oversampling brought the system performance up to 16 bits. Later, Philips invented the 16-bit TDA 1541, but of course they stuck to the noise shaping and oversampling technique because it was working just fine. And then at the end of the 80s, early 90s, they revisited the noise shaping design and said, well, if you can make virtual bits by oversampling and noise shaping, and we can see that chip technology moves into higher frequencies, we can really take advantage of the high frequencies by just oversampling more and more and more and more. And of course the extreme case would be to use only a 1-bit signal and oversample so much that all the other bits of the resolution were virtual. And they managed to do that, and that's the bitstream technology of the early 90s. Now later on, most manufacturers moved away from 1-bit quantizers to about 3, 4, 5, 6 bits, so that the D2A converters you find in chips these days are a hybrid of instantaneous R2R or scaled current source conversion together with oversampling and noise shaping. And we found a nice middle. But of course, it was quite a tour de force to take the oversampling principle from extending 14 bits to 16 bits all the way down to using only 1 bit. And Philips was super proud of it. You see it in all products of this age. Bitstream is stamped in huge logos and letters on every piece of equipment. They were super proud of it. And because of this, they designed some really nice equipment. Now, I can't make this video without taking a moment to honor Ed van Tuyl. Ed was a professor in my university in the Netherlands, and whoever I told that I liked audio, they told me, go to Ed, he will help you out. And as it turns out, Ed worked at Philips for the longest time, both in research as in development. I did an internship at Philips Research in Eindhoven, and literally on the wall there is a 2x1 meter breadboarded prototype of the TDA 1541 and the TDA 1547. This guy was not only clever, but also very pragmatic and very passionate about audio. And I owe a lot to him. When I went to him and said, I like audio, he got me a internship at Research investigating 1-bit D2A converters and Class D amplifiers in one design. Every time I met him afterwards, he said, you know, I'm not doing so much in audio anymore. He worked on USB 2 for a while, and then this and then that. And it would take him literally 5 minutes to just come back to me and say, so what are you doing? What's going on? He told me at some point that he once bought a pair of DSS930s because it's full of bitstream technology that he worked closely on. And essentially this loudspeaker is a labor of love, I think, from many Philips people. And he said, this is the one loudspeaker that I will have for the rest of my life. Which it was. Unfortunately, his life wasn't that long. Shortly after his retirement, he passed away. But I'm very happy to now see his work inside some of these loudspeakers. When we look at the service manual, there's his handprints all over. You can clearly see that this was maybe a commercial product, but mostly it was a hobby project of researchers. And it should have been far more successful than it was. But yep, Ed was very much a big fan of these loudspeakers, and I hope he would approve me making a video about them. So not too many loudspeakers come with their own preprint of a presentation done at an AES conference, but this one does. You can download this from the Audio Engineering Society e-library. Obviously I can't show you more than just the front page, but this is a very interesting document that shows you the design procedure. So essentially what they did is they assumed that they wanted a linear frequency response and a linear phase response, and they started by measuring the drivers. And of course, under the assumption that the filter would be digital, they took the response of the drivers and essentially inverted it in the digital domain to do time alignment using an FIR filter. Apart from all of the high pass, low pass, crossover stuff and an extra bass boost, the only thing they really did was just make sure that the total system of digital filter plus acoustic drivers at the end ends up phase linear as well as possible. What else can I say about this? Quite interesting as well is, I told you before that it looks like a hobby project. There are many measurements done in 1993 with technology at the time with a spectrum analyzer similar to what I had. All of the plots show a timestamp of 11 in the evening, so this is clearly a skunkworks project. Just a quick review here of the block diagram. Obviously, the digital in and digital out is for audio, but it's also for control. We'll look at that later on because it's a fascinating setup. It comes into the control PCB. Audio comes in here into the ADIC, audio digital IC. I don't know. It goes into an DSP, which runs at baseband. This is actually a plug-in board, quite conveniently. Audio then goes into an upsampling filter, and then into the famous bitstream DAC, which is a stereo DAC, of course, used for one loudspeaker. So you have a woofer channel and a tweeter channel. The analog volume control is quite interesting because it's done with a bunch of transistors by the switch control or the central control, essentially. And this central control also sends signals to the DSP, where if you turn the volume up really loud, it will reduce the gain of some biquad coefficients in order to limit the physical excursion of the membranes. Also, I think you can change the DSP coefficients if you have the corresponding preamplifier that I don't have. You can turn the exact acoustic correction for the loudspeakers off, and you can try to do it by yourself with bass and treble. I don't see how that could be better, so I'm not missing that preamp. So after the analog volume control, there's also a tweeter protect. So the tweeter protect knows what volume you have selected. It also measures the actual signal, and at some point will say that's more than enough for the poor little ribbon, and it will limit it. So it's essentially an analog limiter. The amplifiers are extremely classic. if you read the documentation, they go that these amplifiers are optimized for transient intermodulation. We'll revisit it in a later episode, but it's a very classic Class AB amplifier. And the woofer amplifier is a Class G design, which runs off of the same supplies that feed the Class AB amplifier up to about 20 watts. And after that, it will switch over to higher voltage rails. If you remember, a Class G amplifier is essentially a Class AB amplifier with a Class C amplifier on top of it. So the Class C amplifier that extends the amplitude is fed with the higher supplies. And then the two woofers are in parallel with a coil in between, which means that after a certain frequency, only the lower woofer, well, only one of the woofers, I'm not sure this is actually vertically accurate, but only one of the woofers will play the wider range and one of them will play the smaller range. According to the documentation, the crossover frequency is roughly when one wavelength fits across the membrane. So interestingly, this is not done digitally, even though there is the whole song and dance about the only way to filter is digital. But of course, the DAC only has 2 channels, and 3 channels is an awkward number, so they did choose to use an analog crossover here, which is quite interesting if you think about it. And the tweeter is directly driven by the Class AB amplifier. This is also, this whole coil stuff makes me wonder how on earth you can get these 2 woofers to behave phase linearly. But, yeah, it is what it is. Well, I've taken the back jacket off. This is the DSP board. And they are mighty proud of their DSP. Digital Active Response technology. Power amps over here. And these circuit boards are actually really nice. They are mostly one-sided, but the top side is all ground. And I honestly think that I could probably mill a copy of that, no problemo. Okay, I take back what I said about the board being immaculate. It's of course always possible that on connectors you have some damage because people are putting stuff in and taking stuff out. As proven by these pins here, I have no idea how to get this out. But if you look at the solder joints, you will also find that some are damaged. Trying to get this in focus. So the one pretty much in the middle right now, standing loose in the tin. You see a little circle there, and the same happens to one of the bigger LM7805. So it's the big one on the heatsink. This is the back of it, and there are tiny hairline cracks in the solder there. It does make bad contact, and if this is the first thing I find on the first board I take out, I'm going to find more of this stuff. So general inspection is going to be necessary. So there we go again. This thing is put back, it's empty. And this is a bit of a traumatic remembrance of my childhood. I repaired many Philips devices. And the problem is always the soldering. So literally on every plug, on every bit of mechanical interaction, I found little coronae. Actually quite ironic that this 30-year-old device is suffering from corona, but you know, I just, as a matter of precaution, resoldered everything, because back in the 90s I would do it just like that. Now I have a microscope, and under the microscope it did not look good. I don't know what it was. They used some brittle kind of solder paste. I don't know what it is. Obviously on all the SMD components it's working just fine, because these things don't really move mechanically. But anything that moves, it was all loose. So I may want to check all the other circuit boards as well. A few words on this DSS link. It's all described in the service manual. And this is a case of Dunglish like I've never seen. If you're native Dutch, you can probably understand this. If you're native English, you're going to struggle with it, to be honest. As we've already seen, DSS link is a weird combination of an AES EBU signal, frequency multiplexed with a control protocol. And looking at the control protocol already, I can see that it's very similar to the RC5 remote control that Philips uses for their infrared. So it's probably no coincidence that those controls work very similarly. So they're frequency multiplexed, which is fine. By means of a high pass, the audio information will be extracted. We'll look at the schematic for a moment. While the control information is extracted via a low pass filter. So the section down here is pretty interesting. For the control information, you have to see the bus as one long wire. Each bus circuit hangs on this wire and can transmit as well as receive control information. In Dutch, we actually say it like this, and it's literally been translated to English. It's brilliant. So this is where the magic happens, where we extract control from data, and you have to really stare at the schematic for a while to really get it. But the audio signal comes in here, and forget all about everything here. It goes right through here. It's AC coupled. So the AC part goes through a couple of inverters and comes right back out again. It's again AC coupled and right out. So audio essentially goes straight through this DSS bus. Now, at the same time, this thing goes in here to a difference amplifier. And it comes in here from this side after an inversion. So you now have a differential amplifier. So these two data are actually in counterphase to each other. And the way they do a low pass filter is by putting a capacitor across these two signals that are in contraphase. So after a certain frequency, you short circuit essentially the amplifiers and nothing comes out. So this is a very effective low pass filter. Signal comes to this point, gets amplified into digital control 1. At the same time, gets amplified out to DSS out, where it doesn't override the signal because there's an AC coupling there. And the signal that has gone to digital control 1 is being received by the logic. And the logic can also add several more commands to the bus. For instance, if a command would be received by infrared remote control, it would add that to digital control too. So essentially this is an OR gate, gets a little buffering here, and then also goes on that amplifier bus and gets sent along with all the other controls to DSS out. So if a loudspeaker would be master, no commands would be coming in from here, but the master would receive infrared remote control, spit it out on digital control 2, and it would go out by DSS. And the other loudspeaker would not receive remote control commands from DSS2, but would extract them from the DSS input and would send them out to its own controller over digital control 1. It's very clever to take a protocol like AES EBU and frequency analyze it and say, actually there's a lower band that is completely free where we can just stuck in our command protocol. I'm thinking of using this circuit and extracting it. I'm already connecting a logic analyzer to digital control 1 and 2 so that we can look at the protocols when we're sending remote controls into the infrared eye, which is not drawn here. It comes essentially out of digital control 2, out of the logic. So we can send remote control commands in here, then look at this bus and say what this loudspeaker is going to tell the other ones downstream. By analyzing this protocol, I think we can reverse engineer it, and it will be nice to at least draw a specification of it, because I think these loudspeakers need a subwoofer to go along with them, but it would be nice if the subwoofer can, as we Dutch people say, hang on the same bus. Little interim update. Why is this closed? Well, because I have this. The original remote control, found it somewhere online, and turns out, as I expected, that with the remote control you can turn it on and you can get it to play. Also need to redo my terminator, and decoding work will continue. I've fed out the control in and outputs so I can attach the logic analyzer and then simply give remote control commands and see what happens to it. So here we have the electronics. I'm just connecting it to the audio precision. I had it taken out because I was actually repairing the foam rings, but now that I have them out, I might as well do a few measurements. This is connected to the loudspeaker output, so I'm measuring purely electronically and without dummy load at this point. Ground there, woofer and tweeter here, and of course the input is SPDIF. I had to first connect it to the other loudspeaker to start it up, because I don't have the infrared sensor connected here. But then if you feed it a stereo signal and you tell the left channel to be, let's say, 400 Hz and the right channel to be 6 kHz, and you set the loudspeaker to be mono, you can nicely generate test tones for both woofer and tweeter. But what's even more interesting is that by giving it a normal signal, I can actually measure out the DSP response. Because we're not looking at acoustic response here, we're just looking at the compensation that the DSP applies. Which will be quite interesting if we are planning to do our own version of it. Another thing I want to test, and I'll do that in a moment and show you the results, is to give it 0 dB FS digital and try to measure distortion on the analog. So in the listening tests, I do notice when I play the digital signal at 0 dB FS that I get what I think is over-modulation on the sigma delta converter. But of course it could be distortion in the amplifier, it could be distortion in the speaker, or it could be something I'm imagining. And that's where this little boy tells me whether I'm crazy or not.
Whoa, 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 not so fast. What was I talking about? Sigma delta overmodulation? I think I owe you an explanation of what I mean there. So sigma delta is a noise shaping loop. It's a feedback loop that quantizes audio in a very short word length, and by quantizing so grossly makes a huge mistake, but that mistake is being fed back into the feedback loop, and the feedback loop, because it runs at a very high frequency, can correct in the next sample, and so on and so forth. So the errors get smeared out over time, so that's why it's also called pulse density modulation. The problem is, if that feedback loop gets too much input signal, it has essentially no dynamic range or no vertical space to get rid of the errors. Which is why if you give a sigma delta converter a very high level of input signal, the noise floor of the sigma delta will increase. So I decided to look up the datasheet of the bitstream converter, the SAA7350, and if we click on this link, we get a scan. And I think I recognize the scan, so let me look in the document properties. Yeah, you see, that was my scan. I got the paper datasheet by Guido Tent of Tent Labs, and it's, I think, the only copy on the internet. And I was told back at Philips Research that this little sigma delta overmodulation thing is something that most manufacturers aren't proud of. And here it says THD plus N, total harmonic distortion plus noise. And it will be dominated a little bit by distortion, but this is a very nice way to kind of sweep the noise floor modulation under the rug. So at 0 dB FS, the performance is anywhere between 93 and 96 decibels. For digital silence, however, and obviously the harmonic distortion is also absent in that case, the thing can actually perform 103 or at least 100 decibels. So what that means is, for very low or no signals, there is plenty of loop regulation, dynamic range. But when the loop gets full, there is no more room to shape away the errors, and that's why you get, in the final few dB, this is usually between -6 and 0 dBFS, you will see that the noise floor starts to modulate. And I think I also did a few blog posts several years ago where the intermodulation also increases very rapidly in the last few dB. That's typical sigma delta behavior. And it's worse the less bits you have, and well, you can't have fewer than 1 bit if you actually need a signal. So the SAA7350 is very prone to noise floor modulation, and we need to have a look at whether or not that thing runs at full scale, because I have a suspicion that it won't be. Welcome to my own lab notes, because I did this measurement a while ago and I actually forgot exactly what happened, but luckily my notes are very clear. So, investigating the SAA7350, if you remember the block diagram, the audio comes in and goes first through the DSP, then through an upsampling filter, and then straight into the SAA7350. The upsampling filter is the SM5840. And when you select a source, or when you start up the speaker as well, I suppose, you always see a SPI command. Or actually, it's not even SPI. That chip is so old that I don't think the bus was named SPI back then, but they describe what the bus looks like and what bits you have to send. So this is a volume command that gets sent to the upsampling filter, which delivers the data straight into the SAA7350. And it turns out that this is a digital attenuator command. And if you decode the bits, it's always setting a -6.8 dB gain. So, by the way, we're not losing any dynamic range, because the SM5840 is also extending the word length, I think, from 16-bit to 20 bits, if not even 24 bits. So this is actually a very clever system design. The DSP takes 16-bit data, gives out 16-bit data. That was hard enough back in the early 90s. And rather than have the DSP apply the gain and then lose at least 1 dB of word length, you stick it into the upsampling filter, which is there anyway. It's got this digital attenuator, and you just tell it to go -6.8 dB. So what this does effectively is it only uses the dynamic range of the SAA7350 as long as it's linear. So whatever I was hearing at very high input levels, digital input levels, will not come from the SAA7350. It has to be somewhere else. So this looks a bit messy, but these are some of the measurements I did on the speaker output while feeding, obviously, a speed of digital input. And I was trying to get the frequency response, so that later on we have something to approximate it to. But there are some interesting effects that happen here. Let's just look at this curve over here. That seems a fairly clean frequency response. I'm only focusing on the woofer now. Forget this stuff on the tweeter for a moment. But you'll see that when we go up in level, and I one of these, this is, I think, 0 dBFS. You see that the hump here has disappeared. And every time the level reaches a certain threshold, it gets gated down. So what I'm fairly sure is happening here is that a limiter is active. And you have to bear in mind that the DSP board has a 16-bit digital input and a 16-bit digital output. But the tuners have given the bass a boost of several dB. Can I get this in dB? So that goes from -10 to almost -2. Nothing here is absolute. And before you say, hey, the amplifier is clipping, I actually don't have the analog volume turned up very far. I think it puts out maximum 2-3 watts. because exactly I wanted to prevent looking here at the analog amplifier clipping. I'll analyze the amplifier in a different way. I can just feed it an analog input signal and watch the analog output signal. I don't want to go through the DAC at that point. Similarly, I will try to reanalyze this in a digital way by just looking at the DSP board speed of I2S in and I2S out. But this was just a first impression to see if I can correlate some of the things I'm hearing, some weird digital distortion, or some weird distortion. I'm not going to call it digital until I have proof. But this thing looks pretty much like proof. Now, think about this. We're looking at a fixed point DSP. I mean, it's 1992. We're not doing floating point in PCs in 1992, let alone in small digital DSPs. So the tuners have said they need an 8 dB boost. So what happens if you feed in a signal of higher than minus 8 dB, you're going to end up at plus something dBFS. And that's not going to work in fixed point. You'd need floating point to actually encode a plus something bigger than 0 dBFS. And this is exactly what we see here. So I have measurements. I think this is 0 dB. This is minus 10 dB, minus 20, minus 30. Some weird effects here, but I think that's because we're drowning in noise, although I'm still seeing something weird here. I have no real explanation for that, but let's say the minus 20 and the minus 10, they look very similar. And if you go to the gain plot, where all of this is normalized, you will see exactly the same thing. Whenever this thing is linear, curves perfectly overlay. But when the input signal goes out of range, a problem will appear. And that's what you see when you look at the absolute level. So this is minus 10. I think this is minus 8. Minus 7, if I can hit it. Minus 7. Minus 7 gets a tiny little blip. Minus 6, you clearly see here that it gets scaled down. So what I think is happening here, and I'll verify it on the digital, but I do not think I'm wrong. This is minus 3, by the way. This is 0. We have a digital limiter here. We have a digital limiter here. So whenever the signal approaches threshold, and I'll see if I can capture some waveform, you clearly see a sine wave coming in, exceeding a threshold, or coming close to a threshold, because you really can't go over 0 BFS, and it just gets knocked down. So it doesn't get flipped in the classic sense, where you just turn a sine wave into a square wave. You literally gain down. And to be honest, I have nothing against that. I have written several compressors where I do exactly the same thing. I just don't really do it, as hard as it happens here. So for me, this is a very clear case of this was a limit of the technology, and in some way a limit of either the talent of the software coder or just what they could cram into this little Motorola 56,000 something DSP. But we can do better than this. So I am now convinced that this DSP board needs an upgrade, and that I'm going to be the one to build that. We need to figure out a few other things. For instance, the lines the line DSP to host and host to DSP. They're communicating. At least those lines are there. I'm assuming they're for something. So it's fairly certain that they're doing some kind of handshake, and I need to figure out why they're doing that, and then find a way to do the same. This, however, does completely corroborate what I was hearing. I came to the conclusion that when I'm listening to music, I need to set the digital output to maximum minus 10 dBFS, and then I need to gain up the analog volume to arrive at the same level again. And that was clearly happening here. Now on the tweeter side, there's either a similar thing happening, but there's also an analog circuit that governs an absolute level of tweeter power over time. So I'm not sure whether here the signal is changed in the digital domain or in the analog domain. That will become clear when I directly tap into the I2S lines. The interesting thing, however, is that I think back in 1992, not a lot of people were able to attenuate a digital signal. So even with the DSC930 preamplifier, that one did not scale down the digital signal. It was signaling the volume control over the DSS link. It was using the not quite RC5 component of DSS. So it was sending full-scale digital signals with a volume code of, hey, gain this down by 12 dB or whatever. So this would have distorted quite a bit unless you were able to digitally gain down an SPDIF signal. And not many people in 1992 were able to do that. I had a CD player back in those days with a digital output, but I had no way of gaining it. And now it's trivial on a PC. You gain it down. So I can use this and I can play nicely at minus 10 dB FS and then gain it up by 10 dB in the analog domain. But this is interesting because I heard this within a week of ownership, and I've never heard people talk about this stuff. Or maybe in 1992, most of the music wasn't recorded as loud as it is now. Really, I'm surprised by this, that nobody was complaining about this kind of distortion. Okay, here we'll do the isolated test. We've got a sine going in at 42 Hertz, which is exactly the peak of the bass extension. We're running at minus 10 dB FS, and there's zero distortion. Now, if we creep it up, not even at 7, 6 still clean, minus 6 dB FS. But here we go, minus 5 dB. And this is where you can see clearly that when the thing hits, it literally just cuts the amplitude. And it's before the peak, but here it's after the peak. I don't fully understand what this is about. Now, 4 dB FS. It happens literally in every sine wave. So gaining it down before it reaches the peak, that makes sense to me. And then somehow here, probably in a zero crossing, it gains it back down. But what I don't understand is that here we seem to be above the top, but then clearly we do some weird stuff. I have never seen a DSP run a limiter or a compressor algorithm like this. This is weird as. Here in 3 dB, you even see more kinks in the sine wave. But it appears to gain it up and then not. I am super confused, y'all. Now this one is clear. So here it's going up. It hasn't reached the peak. Gains it down. Does that even make sense? From 30 to about 15 volts. Yeah, that's a factor of 2. Literally just gains it down by a factor of 2. Probably goes down through the zero crossing, then does that again. But then what it does here doesn't make any sense to me. To make it even worse, you get several gain steps in one sine wave. Okay, we can actually fix that. This is a 0 dB FS sine wave going in, so it goes up, hits a certain level. Forget about the volts, yeah? I mean, we're looking at an analog signal coming out of a DSP. It gets gained down, it goes up again, appears to cross a threshold again, gets gained down again, goes through 0. But what happens here in the lower part of the sine wave is an absolute mystery to me. But yeah, this is not how you clip a signal. Actually, come to think of it, maybe they're not doing anything at all. Maybe this is not an algorithm. Maybe this is simply choose complement data that overruns, and then the MSB disappears. And this might be the actual zero crossing, and then it flips around. Another hypothesis. The first biquad is the one that does the 42 Hertz peak. It overflows the two's complement data notation. You get weird data out. But you'll never see that because it goes through another 10, 11 biquads. I don't know how many there are to create this frequency response. And because of that, you cannot make sense of any of this data. You're not looking at the very last stage of the data corruption. But yeah, this is not good, people. This is broken DSP.